In this video, I will demonstrate how to use the magnitude method for calculating the electric field strength and direction at point A due to one or more charges. But first, I will explain the concept of a field by using Earth's gravitational field. Here is a picture of Earth as seen from space and Newton's formula for the law of gravitational attraction. This formula may be rewritten to express the value of the gravitational attraction, that is, the g value, as follows. This part of the formula calculates the force on a small test mass. This force represents the test mass's weight. G is the gravitational constant. I have used a lowercase m to represent the test mass's minuscule mass, while using an uppercase M to represent the large mass of Earth. Note: this technique is usually used in electrostatic problems by representing a small charge by a lowercase q and a large charge by an uppercase Q. One last item in this formula is r, which is the distance between the test mass and Earth's center of mass. After dividing both sides of the equation by the mass of the test mass, we arrive at the following formula for the expression of Earth's gravitational field. This gravitational field can be visualized with arrows pointing to Earth's surface. So, here are the important concepts about fields. 1. The direction of the field lines indicates the direction of the gravitational force exerted on a test mass. Therefore, Earth's gravitational fields tell us that object released above Earth's surface would travel towards Earth's surface in a path parallel to that of the gravitational field. Note: we are assuming the object does not have any horizontal motion, only vertical motion. 2. The number of arrows, that is, the field lines, gives us an indication of the field strength. As the number of field lines increases, the strength of the gravitational field also increases, and vice versa. For example, due to the moon's low mass, it has fewer gravitational field lines. 3. At this moment, you do not see any test mass above Earth's surface. So, some students mistakenly believe that the gravitational field do not exist. That a field only exists when a test mass or test charge is present. No. Even though you cannot see the field does exist. The only way you will notice the gravitational field is by the effect it has on a test mass. For example, if I stand by my desk and release an apple, I will observe it falling straight towards the floor. Now, if I look at the back wall of my classroom, I will not see any gravitational field lines. However, I can prove that these lines do exist by walking to the back wall and then release an apple, which of course falls towards the floor. The above concepts also apply to electric fields with some modifications involving how we represent the direction of the field lines based on the sign of the charge. Electric field lines always point out from a positive charge and always point in towards a negative charge. Now, let us turn our attention to the calculation of electric fields created by charged objects. When using the magnitude method for calculating electric fields, you just need to carry out the following steps. Step 1. Start with a diagram showing the position of each charge in meters, the value of each charge in coulombs, and the location of point A. Step 2. Use the following formula to calculate the magnitude of the electric field strength at point A due to charge Q. Note: all the values used in this formula are positive. Step 3. Once you have the magnitude for the electric field strength at point A, you must now determine the direction of the field, that is, which way does the arrow point. You do this in the following manner. A. Draw a diagram with charge Q and point A. B. Draw a straight line between charge Q and point A. C. Looking at charge Q and the line you just drew, which way should the electric field line point? Now, draw the electric field line. Note: if the electric field line, which is a vector, is a diagonal vector, then it must be broken up into its xy components. In previous problems, we have done this using the following formulas. Step 4. Repeat steps 2 and 3 for any other charges in the problem. Step 5. When you have calculated all the electric field vectors, then you add up their xy components to obtain the magnitude and direction of the net electric field vector. In previous problems, we have done this using the following formulas. Let us now do some example problems. Note: to make this video short, I am avoiding problems involving diagonal vectors. Here is problem number 1. You have the following configuration for two charges and point A. The location of each is given in meters. Calculate the magnitude and direction for the net electric field at point A due to charges Q1 and Q2. So, following the steps I gave you, you would do the following. Step 1. Draw a diagram of the problem. Step 2. Calculate the magnitude of the electric field at point A due to charge Q1. Here is that calculation. Step 3. Determine the direction of the electric field at point A due to charge Q1. So, I have drawn the two items of interest. Then, I draw a line connecting these two items. Now, looking at the negative charge, I know the electric field line should point towards the negative charge. Therefore, I draw the following arrow. This arrow is in the direction of negative I hat, and so, the electric field at point A due to charge Q1 is A negative 2.88 times 10 to the fourth power, Newton per Coulomb, I hat. Step 4, repeating steps 2 and 3 for the electric field at point A, due to charge Q2, gives the following. The magnitude of the electric field at point A due to charge Q2 is. The direction of the electric field at point A due to charge Q2 can be determined from the following diagram. Now, I draw a line connecting the two items of interest. Looking at the negative charge, I know the electric field line should point towards the negative charge. Therefore, I draw the following arrow. This arrow is in the direction of positive I hat, and so, the electric field at point A due to charge Q2 is. The positive 2.40 times 10 to the fifth power, Newton per Coulomb, I hat. Step 5, I calculated the net electric field at point A, due to charges Q1 and Q2, to arrive at the following answer. The positive 2.11 times 10 to the fifth power, Newton per Coulomb, I hat. Now, I will give two more examples without audio commentary.